Here is the pointer. Okay. Hello everyone. My name is Vishwa Pratap Singh. So today we will try to understand basics of crystallography. So let's start. So here are some images from nature. So the particular top left image is from crystal. These are kind of gems, stone or quartz that you can see directly in nature. So you can see here the flat surfaces, particular edges. That seems that uh, uh, someone has created, but not these are not created by some human being, but these are available naturally. Also, these are also these quartz crystals and representing the crystal structure in nature. Here we have hexagonal. You can see different structure here, and further this image representing the frost, the snowflakes from snow. So these are having hexagonal structure, and the nature actually try to stabilize the uh, like nature seeks stability and with the less energy. So in that case, uh, the long range order of in snow, you will find that these snowflakes are repeating. And same way, this is the eye of gene. This is the eye of gnat. Gnat is a kind of bee. So someone has taken this image with the help of microscope. The microscope, generally they have used scanning electron microscope to see the pattern of this gnat's eye. And here you can also find that to a better visualization or better much more area capture, the nature has created the eye of this V in the kind of hexagonal structure of this particular block, and then it is repeating for a long range order. And same way here you can see the sunflower disc forels. This is a sunflower, and here the pattern is kind of Fibonacci kind of pattern, and the blocks are repeating to develop this structure. So even though these are not, this is not a crystal, this is also not a crystal, but the there is a kind of symmetry, there is a kind of pattern that we can see in nature in daily life. And these are also crystals. They, if you will break, let's say you have a bigger block of crystal and you will break it from anywhere, you will find these type of edges and these type of surfaces. So that represent that nature also, uh, the thing that matter available in nature, whatever type it is having a some kind of structure, some kind of pattern, some kind of symmetry. And there are some matter also, some material also, those don't have some kind of symmetry. So researchers have classified them with the different structures. So here is the this periodic table. So the periodic table representing the elements, and here you can see iron is having BCC, body centered tetragonal, and then you can see hydrogen is having simple hexagonal, and these alkali metals, lithium, sodium, or potassium having BCC structure. So the whole periodic table is have some kind of crystal structure, and some of materials don't even doesn't have defined crystal structure. The research is still going on. So and the the crystal structure in this periodic table are on the standard temperature and pressure, because with the temperature application or pressure application the structure changes. So let's say you have, why the crystallography is important. Let's say you have a iron, and then uh, you want to make some kind of compound with a iron and chromium, or let's say you want to make some kind of compound with copper and iron. Then see, copper is having FCC and iron is having BCC. So that means if we will mix them, uh, then there would be some other structure, and that structure need to be studied to what kind of property would be there, or what property would vary. So to understand this, we have to study the crystallography. So on the basis of those all long range order of the particular blocks, and then there is no long range order of particular blocks, we have uh, different of materials. So these are crystalline material, the quartz, those are crystalline actually, and they have long range order. And then we have polycrystalline, that are combination of both amorphous and crystalline. Amorphous are those that are like, in if you will see in real life, the glass that seems to be smooth, but it has no long range order of these particular blocks. So how we can observe these crystal structure of particular material? To Because with your naked eye you can't see the crystal structure of particular material. Let's say you have your mobile phone, you touch the screen, but you don't feel, you feel like it's too smooth, and you will not identify what's there and what kind of structure is there. And but if you will see your fingerprint, then there is just some kind of pattern also. But because we are able to see it with our naked eye, and with the light, with the help of lights, so we are able to look at it. But for those for the materials, in case of materials, the pattern or the blocks that form these patterns are so small. For this you need to have some special devices. So those special devices are electron beam based devices. So on the basis of those devices we have these images, and with the help of these images you can see that how the material having crystal structure formation, or which structure is there. So let's see, this material is there. So you can see here there is no any visible pattern, but this side you have some visible pattern. So you can say that this material having this structure. And then we have a nickel oxide rod, nanorod. You can see when the scale is around 100 nanometer, means like you need to zoom out much more to increase the magnification, and then you can see how these blocks are in long range order to make a particular structure. Further, you can see the silicon is also a material that can be found in amorphous silicon, also in crystalline silicon. So this is the particular silicon image taken by the ICM, sorry, HRTM. So in this image, you can see the differentiation between amorphous and crystalline silicon. Further, we also have the other images from copper oxide to understand how these shape could be. So you can see that this is kind of cubic shape, and further there are other shape also. This is kind of different shape and kind of hexagonal shape here. It's a kind of tetrahedral. So these are different shape that you can see with the help of those devices that are using electron beam. So to understand or to classify these and the properties, we will discuss much more in depth. So what is the unit cell and lattice? So you can see that the particular this point can be repeated in y direction, or also x direction. So if you will repeat them, or you can say this is x or this is y. So this point is repeating in the x direction and y direction, then you will have a particular unit. So this particular building block, or you can say the unit, that is covering the four atoms. So we can call them atom, or you can call them point also. So let's say these are these these are points, and with the help of these points we can make like this block. You can make, you can repeat it here also, you can repeat it here also, you can repeat this side, and then so it's making kind of lattice. So the whole structure is the points making this kind of net. It's called lattice actually, and this is called unit cell. The the main building block, the smallest unit. And so the this smallest unit can be divided into uh, can also be divided on the basis of two categories: primitive unit cell or non-primitive unit cell. So let's say if you, this is the smallest unit and the atoms are all only on the corners. But what if you have one atom, like let's say the my pointer is here and then it could be here also. So in this case, the primitive one is only this, which doesn't which which doesn't have the atoms on the edges or in body center or wherever. So let's say if you will think about the primitive unit cell, the only corner it would have only have atoms only on the corners. But if it has a the atoms on the body center or on the face or edge, then uh, it would not be a primitive unit cell. So that would be called as non-primitive unit cell. And this this unit cell can be represented by the direction or by the vector. This vector you can see. So here h and k are actually integer. If you will think about the three dimension, then we have this unit cell, because in case of three dimension, the smallest unit we have this one. This is not actually uh, uh, pure cubic, but is a kind of triclinic. So we will further understand it. So in particular this unit cell, how many atoms are there? So to calculate these atoms, either you can you can visualize them, or and then you can calculate, or we have also this formula. So with the help of this formula we can calculate the number of atoms inside a particular unit cell. So we have this, the number of interior atoms, the number of face atoms, the number of corner atoms. So with this, we can come to know that how many atoms are there. And what is coordination number? So let's say you have some atom and surrounding it, the nearest atoms are called, the number of nearest atoms is called as coordination number. So this atom is there, and at a particular distance, let's say x, and then x, then x, then x. So the distance from this green atom to the yellow one, the distance is same. So that's why we are calling the coordination number is 4, because it has a 4 nearest atoms. Then this one is having 8 atoms, nearest atom, so we are calling it coordination number 8. And the another thing is atomic packing factor. So the unit cell is made up of atoms, and we need to calculate how much volume the atom are, like atom also have their particular volume, and also the unit cell also have a volume. So how much percentage or how much volume the unit cell is uh, occupying inside that unit cell, we need to calculate that. So that unit cell, that uh, uh, that space or whatever, we call it atomic packing factor. So the 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 atoms are packed densely, or you can say they are close packed. So this is simple cubic. Here you can see uh, we have atoms on the corners. So these atoms are actually participating in 1 by 4th, because you have four corners on the upper plane and then four corners on the lower plane. So on the lower plane, the every atom is participating to this cube 1 by 4, and also this one 1 by 4. So that means we have four atom, then you will do 4 into 1 by 4. So you will get one atom. And to calculate the atomic factor, atomic packing factor, you need to calculate the volume of uh, atom inside this unit cell. So we have only one atom, and because the A is equivalent to the dimension of this cube, and then R is the radius of this atom. So we can calculate the relation between A equal to A and R. So this is A equal to 2R, and it's much more visible, so we don't need to think much. And then atomic factor can be calculated with the help of an atom, and then we have this volume of particular atom. So how we can calculate the volume of atom? With the formula of volume of sphere. So we have this sphere volume here, and R is the radius, and then we can divide with the uh, volume of unit cell. So that's the volume of cube, and then we come to know the atomic factor is around 0.52. Or if you can multiply, then you can say that the unit cell is occupied by the 52% of unit cell is occupied by the atom, by the atoms, and rest of is empty. And the further you can see the coordination number. So let's say in case of this, we can understand from here. So let's say we want to calculate the coordination, we want to calculate the number of coordination number for this atom. So here you can see this one is nearest one, and then this one, and then this three are nearest one. But if you will see this is the diagonal, and the distance between this and this diagonal have far away. So the case is for this also. So only in this case, if you will think only one building block or one unit cell, you will have three, coordination number. But that's not the case, because this unit cell is uh, repeating for long range. So you have many cubes around it. So let's say you have this cube and this, then you will have uh, how many atoms near this atom. So let's say this is the one, then you will have this one, then you will have two, then you will have three, and four are here. And then if you will see the downside, then there is a one, and then another one on the upper side. So you can understand this way. They are the coordination number of this atom is 4 inside the simple cubic. Further, we have this body center cubic. So in this case, the structure, the unit cell is almost same, but the one atom is uh, inside the unit cell on the center. So it will, how many atoms it will have? Definitely one is inside, so it will have one, and then 1 by 4, like each is sharing 1 by 4, like a simple cubic. And so we will have two atoms inside this. And how we will calculate relation between A and R? So let's say these are actually touching each other, the diagonal one, this will touch this. So the atom uh, body centered one touching each corner atom. So when they are touching it, but these corner one are not touching each other. So how we will calculate it? So we can see, if you will draw a line diagonal through the uh, cube, you will come to know that this is also touching it, the body center, the lowest left corner one touching the body center, and uppermost right corner also touching the body center. So we will draw a line, and we will see that the R plus 2R, the radius, diameter of this whole body center atom, and then R, so it would be a 4R. And then you need to calculate this is the plane. If you will think about the upper plane, so how you can calculate this? So this is the one particular triangle. You can see, I can make let's say pen. So this is the atom, this is the angle that we can have. Okay, so we need to calculate this one. So this is we need to calculate this one. And how we can calculate this? So to calculate this, you already have this one A, and then you have this one. So you will get this, and with the help of this, you already have this, and you already have this, and then you can use the trigonometry, and you will get the A equal to 4RY under root 3. So now you got the relation between A and R. Then you can calculate the volume of the unit cell, and then the volume of atom is already known because the radius is 4, and then there are 2 atoms. So we got the 68% packing by the atoms inside this unit cell. So it's a much more packed as compared to simple cubic. Then move to face centered. So here what is the issue? So we have already these uh, uh, four atoms like a cubic, simple cubic, but on the faces also, on case of, if we will see, these are faces. So in this case we have four atoms on the faces. So these atoms are sharing only half, because see, there would be also in this side there will be another unit cell, and this is only the current unit cell, so it's only half, sharing half part of this atom. So in this case, how many atoms there? So half of this and half of this, there will be one, and then half of this and half of this, there you got how many? 2, and then this half and this half, you got 3. So there are 3 from the 3 atoms from the face centered, and 1 atom from the corners. So how many atoms you will have now? You will have 4 atoms. So you will have how many? 4 atoms. Now how you will calculate the ratio between R and A. A is actually the dimension of this cube. You already know. So how we can? It's easy actually. So we can find that on this plane, we can have this diagonal, and then we can have this complete triangle. So there is a also this A, and then A, then you can use trigonometry, and you can find the relation, because this is actually 4R. So this is actually 4R again. So this is also 4R. Now you can calculate easily, and we got the relation between this. So after calculating this atomic packing factor, we come to know that the atoms occupy much more area, much more space in this unit cell. It's around 74%. Next, there is a close packed rhombohedral, like actually uh, this is a kind of hexagonal close pack. So SCP we call it in short. So we have this, where is the pointer? So we have this A, and then B, and then C, and then you will repeat it up to 9 layers, and this is the base, and then the body centered one, and then the C also. So we have 3 units in this case. So here you can see this is kind of SCP. So let's move on. So this is the SCP, hexagonal close packed. So in this case, we also need to calculate the APF. So how we can calculate? So this base is the hexagonal, uh, and the dimension of one A to B is A actually, and now you need to calculate the height. So height, how you can calculate the height? Because see, this is A actually. Here you can see this is A, and okay, I can't write because I don't have pointer, I'm using mouse. So it's actually A, and then you can put this here and this here also. With the help of this triangle, you can calculate, so see, this angle is 120, this angle is also 120, and then you will have 60, 60, and you will also have this one 60. So now you can calculate this distance, and once you have this distance, then you can easily calculate height with the help of this triangle. Okay, so in this case, if we will see, uh, and the case is here, actually see this is actually close pack. So in this case, what will happen, you will have like this type of triangle, and and you can understand from here. So see, these actually are touching each other. So you already know the relation between a and a is equal to 2r. Now in this case, so we have the relation between a and 2r, but we need to calculate the height to calculate the atomic factor, or also how many atoms are there. So let's first calculate. Okay, let's calculate. Let's understand this one. So the relation between the height and the relation between the height and this dimension, this one, the relation is this, and you can use this triangle to calculate this one. That's quite easy. I use geometry. And how many atoms are there? So we have this atom and participating 1 by 6 times, 1 by 6 times in this unit cell, and this is participating completely, yani means it is participating fully, and then this is also 1 by 6 times. So there are how many? 1, 2, 3, 4, 5, 6. So 6 into 1 by 6. So it would be here 1. Also this base one, corner one 1, and then 1, 1 and 1, 2. So the base and upper plane are giving you the with the corner giving only 2 atoms, but there is a one face centered also, or another one on face. So this will give half and half 2. So there are 3, and then you have already 3 on body center. So you will get how many? 6 atoms. And then you can, with the help of this, this is well known relation between this height and the this dimension. So this relation can be used to calculate the atomic packing factor and volume of atom, also unit cell. So when you will use this, you will got the 74%. It's almost equivalent to the FCC. So in case of hexagonal SCP, we also have atomic packing factor around 74%. So finally, we come to know that there are some material having FCCs, there are some BCC, there are some SCP. So we have a very known gold. It has a FCC, and it has a high melting temperature also, mostly because of higher density, due to atomic packing factor. And BCC iron, there is a BCC, and so see, the titanium is most hard material as compared to these, and it has a like close packed HCP1, so it is much more dense, and the density is also depends on the radius of the ionic radii. So there are various things need to understand, but roughly you can say that this one FCC and HCP are much more dense as compared to BCC. So in case of to understand these lattice, uh, we have a Bravias lattice. So this is the comes from the name of a French scientist. So he actually used geometry and mathematics to understand how many systems we could have in a space. Like if you will see in a space, you will try to figure out how many pattern there would be that can be infinitely repeated to get uh, to get a particular material. So let's say, so as a generally, if you will think, you will be amazed that there are only 14 unique way by which uh, you can present the every matter, uh, you can present the every matter and repeat endlessly in 3D space. So there are only 14. So why these are only 14? So there are kind of symmetry that govern these Bravia lattice. So we have this first one, rotational symmetry. So in this case, what you can see, you have this line. If you will rotate it at 180, the it will be always same after even 180. So here what we need to check, there is a kind of 2 pi by n. This in this case 2 pi by n case, so we are taking 180, so that's a pi. So 2 pi by n is actually the n times fold rotation. So 2 pi by n actually. So in case of 2 pi by n, you can see, uh, if you will divide, if the if anything or any structure or plane, any structure, after every 180 rotation it's coming in its original position or original visualization, or it looks always same after rotation at 180-degree, then you can call it two-fold rotation. But if you will rotate it at let's say 90-degree, and then it looks same again, and then you will divide 2 pi by 90, so you will come to know that it's a three-fold rotation. And in case of 4, uh, no, there is a mistake actually. This is 120. 120. So in case of triangle, you need to check. So you need to, if you will rotate it at 120-degree, then you will get the same look every time. So in this case, if you will get the same one, then you will call it three-fold times, because if you will divide 360 by 120, you will get 3. So it's a called three-fold rotation. Let's say we have a square, and if you will the square, you will rotate it by 90, and every time you will get the same you will get the same look. So that you will that same look is at 90 rotation. So if now you will divide 2 pi by 90, like 360 by 90, then you will get 40, you will get four-fold rotation. So in this case also star, this is the kind of star. So there it has a rotational symmetry, but mm, the this butterfly, if you will rotate, then you are not getting, see, this one and the second one, you have rotated it at a 90-degree, like clockwise, but you still didn't get the same, you the it's not looking same. You will say that it's a tilted at 90-degree, but it's not same. But here, if you will rotate at 120-degree, you will find it same. And then you rotate it at 180, the structure is changed actually. And then again, the structure is not changed, the orientation changed actually. But in this case, the orientation is always same. So it's called rotational symmetry. You will rotate it at a particular uh, at a particular angle, but still you got the same. So you will divide that by that angle, you will divide 360 by that angle, and you will get the how many fold rotation is there. Then comes the mirror symmetry. So in this case, the mirror symmetry is that, so we have a particular plane, and you can see you can see yourself in a mirror, or this, or in this you can see this plane. So this butterfly is both side of this plane is similar. So this is called mirror symmetry. Also see in your hands, there is a mirror symmetry. But let's say these This is also mirror symmetry case, but if you have this kind of the drop fall on the surface, so uh, it doesn't have mirror symmetry, because here you can see this, but this thing is not here, so this is also not here. So that means you can see there is no symmetry. Further, there is a inversion center symmetry. So how we can understand this inversion symmetry? So let's say in case of this uh, caricature, you can see we have this point. So if you will take this point and to this point, you will find that this is having same. So you will invert it and then you can find it same as a particular point again. So look at this and this. So in this case, you can see this corner is similar to this corner along this point, and this corner is also similar along this point. So here you can understand the inversion center symmetry. So you can also think, let's say if you will have kind of this is a sign and I have some point here. So this point is there, but what if I will draw this? Then you will have inversion symmetry, and this is there. If I will delete it, let's say if I will delete it, I am deleting it. Let's say I deleted it. Now it doesn't have any inversion symmetry. So this is the case of inversion symmetry. And then we have this rotational inversion symmetry. So you will rotate thing and then invert it. You would get the same. So you would get the same. So combination of rotation, this one, and inversion. Then you got the rotational inversion symmetry. So on the basis of those symmetry, we got the 14 Bravia lattice, and here you can see triclinic. The triclinic is here, and triclinic clinic doesn't have any symmetry, so it's all only found in one. Hexagonal has 6-fold symmetry, uh, and like basic cubic, the cubic one has a 3-fold rotation symmetry. So in all cases, so that's why we are getting simple body centered and faces centered. So this is the thing due to the symmetry. Symmetry is actually filter, so it filters out these crystal structures. Further, we have Miller indices. So how we can find the Miller indices? To find the Miller indices, we have uh, we can work out on the Cartesian plane. So this is a Cartesian plane on which there is a this is the plane that is cutting all the axes on a uh, particular point. So this point is represented by 1 1 1. So you got the coordination number 1 1 1, and when you divide them, these coordination number by when you divide these coordination number 1, these are coordination number. So to calculate the Miller indices, you need to do what? Okay, let's understand it in another way. So you got this coordination number. Now if you will make them one, let's say if you will cut at x and here y and then z. So what you will do, you will get x here, y here, and z here. So what you will do, 1 by x and 1 by z, sorry, y and 1 by z. So this way you will get the Miller indices, and you can put them in this parenthesis. So we called it as a, we can represent this by this. uh, a parenthesis and then put this, uh, close it, and this represent the crystal plane. So in this way you can find this Miller indices. Further we can see this is the plane parallel to Z and Y. So it is cutting at coordinate 1 but not cutting Z and Y. So we think it will cut at infinity, so we can put infinite here. And again, according to this rule, you can divide 1 by 1, 1 by infinite, 1 by n. You got the Miller indices like this. So this is, you can represent, this is 100 plane. Further, so again the thing is that the similar way that I have shown this. So here it's cutting at 1 by 3, 1 by 2, and at coordinate number at 1. Sorry, not coordinate number, it's a coordinate only. So here how you can find it, so we got this, but how the same way you need to 1 by 1, then 1 by 1 by 2, and then you will get this. So here we got the whole integer. So the main aim is to get the whole integer. So here we got these Miller indices, and these are notation. You need to follow these notation. Let's say if you have crystal plane, then you will use parenthesis. You want to represent equivalent planes, then you will use curly brackets. And if you want to use, then you can use these brackets, what we call them, the uh, square bracket, or so these can be used. And in case of hexagonal system, you use the plane and the direction. So here we have, because see in this case we have HKL, but there is another case I. So let's say if you will see where is the case. So in this case you need to use this, there is a let X Y and then another one diagonal one. So this represent the I actually. Okay. So these things can also be represented by the vector u, v, and w are actually coordinate cut by the plane at particular axis, and a, b, c are representing the vectors direction. You can think. So how you can calculate the interplanar distance? So for the cubic one, you can directly calculate using this. You can use this uh, vector. And for general case, like let's say you can have triclinic, then you can use this one. This is the calculated with the help of the vector. Also the Bragg's law, this is most important for the XRD. We don't, this is actually no need to understand here, we can understand it later. And angle between the two direction, let's say you want to calculate the angle between two planes, then you can use this formula. And to understand this, you need to know about the geometry, vector geometry actually. So what are the application of these Miller indices? So the application of Miller indices is in the device fabrication in electronics, CMOS or MEMS. So silicon wafers are actually kind of cylindrical, and then they cut to create the base, and you got the very thin layer, very thin surface layer. That layer is called silicon wafer, and these wafers are actually having so they have their particular notation in industry and in academia, so they can represent it by 100 or 11. So in this case you can also you can see that how the wafers are flat surface and secondary flat surface to know which type of uh, which type of semiconductor is there. So in this case, if you have a, let's say So if you have two flat surface, so one primary one, or if the it has only one flat surface, this cut, this is kind of uh, circular, and then there is a cut. So this kind of cut is called flat, primary flat. And if you will have at 45 degree, then this only one cut, that is a primary flat, you will represent it 1 p type. And if you will have a uh, two cut, one is at primary flat, and then another cut is at 45 degree. So now you will call it 1 but n type. And then further, if the secondary cut is, or secondary flat is at 180 degree, you will call it 100 n type. And primary flat and secondary flat are at a part 90 degree, then these are called 100 p type. So these are actually notation. So Miller indices are important in device fabrication. So this is the thing that we have understood it. For any question, you can write those in comments, and we can have further discussion in comments. So thank you so much. Bye bye.